Good evening. My name is Navatan Zirania. I'm from Group 25. We were given the topic of reinforcement learning, and I'm going to give you a detailed breakdown of what it entails. Yes. So, so an introduction to reinforcement learning. Reinforcement learning is a branch in machine learning that involves an agent taking actions in an environment to optimize rewards. So it's generally a branch in machine learning where an agent learns to make decisions by interacting with the environment to maximize rewards. These rewards are in form of penalties, and it relies on feedback and sometimes trial and error. So to show you how reinforcement learning works, or framing a reinforcement learning scenario, an agent takes actions in an environment, and this is interpreted into a reward and a state representation that are feedback to an agent. Yes. So how it works is that an agent takes, in simple terms, is that an agent takes an action within an environment. So these actions result into rewards. Sometimes the rewards are positive, sometimes they're negative. So therefore, the state changes the state of the environment. So when the state of the environment changes, an agent learns from this feedback that I should either make better decisions with time, or I'm going to stick to the decisions that I've made. Yes. So this, as you're going to see this diagram, as you're going to see this diagram, here an environment. It shows you the environment, the actions, the reward, the state, and an agent. So it's sort of a learning loop, that continues until an agent develops an optimal strategy or policy to achieve a better cumulative reward with time. Yes. So, um, yes. So I'm going to take you through the concepts in reinforcement learning. So here we have the agent, the environment, the state, action, reward, policy, and value function. So in simple terms, an agent is a learner or decision maker, and this is the person that interacts with the environment. Yes. So the environment is a system that the agent interacts with. Yes. Then we have an environment. An environment is a system or world in which an agent operates. The state is a condition of the environment at a given time. Yes. Then action. An action is a move or decision made by the agent. Yes. Then a reward is a numerical signal received by an agent after taking an action. Then a policy is a strategy followed by an agent to take an action. Then a value function. This is a measure of expected cumulative reward. So here the agent can get from a given state under a specific policy. So generally, the goal of reinforcement learning is to learn an optimal policy that allows an agent to maximize the reward that we talked about. Yes. Then let's look at the types of reinforcement learning. So we have model-based and model-free algorithms. Those are the two types of reinforcement learning. So model-based algorithms, here the agent is able to predict the reward of an outcome and take actions in order to maximize the reward. It's also referred to as a greedy algorithm because its major goal after decision making is to maximize the rewards that are given. So it's used where there is complete knowledge about the environment and the outcome of the actions in the environment. So in simple terms, model-based algorithms are predictable, first of all. They are well understood, and they are very efficient in decision making. Yes. So when is model-based reinforcement learning used? It's used in circumstances where an agent has complete knowledge of how the environment works, Yes. So also it's also used when the environment is fixed or static. So that means it doesn't change unpredictably over time. Yes. Then we're looking at types of reinforcement. Another type of reinforcement learning, we have the model-free algorithms. So here, the agent carries out multiple actions multiple times and learns from the outcomes. Yes. So unlike model-based reinforcement learning, model-free reinforcement learning does not require an agent to have prior knowledge of what the environment entails. So instead, the agent learns purely from experience by interacting with the environment multiple times continuously. Yes. So the key characteristics of model-free algorithm are that the agent carries out multiple actions and learns from their outcomes, as we have seen in the definition. The second characteristic is that it develops its own action or strategy to optimize its own rewards. So another one is best suited in dynamic and uncertain environments where complete knowledge about the environment is not available. Yeah, so a real life example of how reinforcement learning algorithms work is that, let's say we have a self-driving car, like those we see in the movies and all. Yes, so if a model-based reinforcement learning is used, it might prioritize reaching the destination faster. So it's going to prompt a car to run over a person because its major aim is to reach its destination in time, because it's focusing on maximizing the reward. What am I getting when I reach there in time? Yes. So, which is not in model-free approach. In model-free approach, it's the car learns self-driving strategies over time. So it ensures that it waits maybe for like pedestrians to cross the road or maybe for the road to clear so that it can reach its reward or reach in time. So it follows optimal ethical decisions, unlike model-based algorithms. Yes, I hope I've explained it well. Then, looking at reinforcement learning techniques, we have the Markov decision process. It can also be referred to as the MDP. So the MDP is a mathematical framework for decision making. So here, the outcome of an action entirely depends only on the current state. So we don't focus on the past state. We focus on the current state of the environment to make a decision. Yes. Then the Bellman equation. Okay. Then the Bellman equation. The Bellman equation is what is shown below, the image below down there. Yes. So the Bellman equation focuses on values functions in reinforcement learning. So it's basically a formula that is used to compute optimal policies and value functions in reinforcement learning. Yes. Then dynamic programming. Dynamic programming is a method used for solving real complex reinforcement learning problems. So here we break down the problems into simpler sub-problems for easy decision making. Then value iteration. Value iteration is this second formula that is shown above here. Value iteration focuses iteratively updating the value function until it converges to the optimal solution. Policy iteration is a two-step process where policies are evaluated and improved iteratively. It's in the name, iterating. So you keep on changing in order to get the best decision, to optimize the best reward. Then Q-learning. Q-learning is a model-free reinforcement learning algorithm, yes. So it learns that value of an action in a particular state, aiming to maximize a reward. Yeah. Then I'm going to give you a detailed description of the Markov decision process. So I told you in the previous slide that it's a fundamental framework for modeling real for model sorry excuse me for modeling reinforcement learning techniques. Yes. Here, decisions are made sequentially over time. Yes. So an agent, let me show you this. Yes. So the key characteristic of Markov decision process, an algorithm makes a sequence of decisions that interact with the environment over time. So here, the environment state changes based on the agent's actions. So whatever you do depicts what decision you're making. Yes. So the rewards are assigned after each action, guiding an agent towards a better strategy. So the decision-making process follows the Markov property. The Markov property basically says that future state depends on only the current state. We don't involve the past states. Yes. My colleague is going to come and take you through the rest of the detailed explanations of the reinforcement learning techniques. Yes. Thank you very much.
Good evening to you. So I'm going to start by taking us through value iteration. So just to give you a brief summary, my colleague already spoke about some of these things, but for value iteration, what we have to know, it deals with optimizing the value function. Let me say we've gotten a particular value when the environment was in a given state after carrying out a given action. So we have to continue iterating that particular value until we reach an optimal value or state. That's just a brief summary. So yes, so the value is computed using an iterative process. Now, for policy, just like you hear the name, remember when this agent is going to take the actions in the environment, there's a policy or a strategy that it follows, like a type of rhythm that it follows to carry out these actions. So here, basically, what we are doing is we are dealing with the policy. So we have to take action, like to change the policies, to adjust, to manipulate, all those things. But this is done to the policies so that we can get a policy that enables us to get an optimal path, optimal solution, or optimal value in the end. Like you can see, so it has two phases. We have policy evaluation. So basically what we are going to do here first is to compute the values for different states of the environment using this given policy. Then the second part is where we improve the policy. We first monitor the value. Then we deal with the policy, we improve it so that we can reach an optimal value. So now I'm going to be taking us through some real-life applications of reinforcement learning. So we have NLP, natural language processing. This is where we have things like ChatGPT, chatbots, and all those AI features that we might be using on our phones, like Gemini, which is in Google. Yes. So it enables us to communicate with these chatbots or to use them. Their mere existence comes about by natural language processing, then also summarizing long texts. For example, you could have a piece of work that you want to get summarized. So, of course, you put it in the chatbot. Then we have healthcare. Now, for healthcare, there are so many circumstances. For example, we have drug discovery, because these computers, machines, robots, whatever you want to call them, after learning, remember they're going to be fed data and they're going to learn from it, get the patterns, then they'll start to take actions basing on the policies or the strategies that they've found. It could either be in a model-based way or a model-free, but still we can conclude that they'll be able to find the discovery of a drug by this continuous learning process. So another application in the healthcare is that we can train these robots to actually perform surgeries and then even to improve disease diagnosis. So now the next part is robotics and industries. So we've already established that in reinforcement learning, we are dealing with an environment, we have an agent, we have a state, we have a policy we have to follow, then we have a value that we have to get at, or a solution or optimal solution. So in robotics, robotics basically deals with deep reinforcement learning. So we know robots are the way they work or the way they operate, they're going to learn from something. Then they're going to take that knowledge and carry out a task or carry out an action. But with time, after learning, they may start to perform some actions on their own. Now, it's all reinforcement learning. So, next, I'm going to be taking us through the implementation of the Markov decision process. So we have, let me just show you the concepts within it. We have the state. We already know that's the condition of the environment at a particular time. We have actions. These are just moves or available moves that can be taken in that given state. We have transition probabilities. So this is basically the probability of reaching a new state after taking an action. Then we have rewards. Now, this is what is gotten after the agent has taken an action within an environment. It could be a reward, it could be a penalty. Now, penalty, for example, I want to give an example. Now, in real life application, we have a game of chess. That's where we can actually apply reinforcement learning. That's why we have value iteration and policy iteration. They all fall within chess as a real life example. So now, for example, we have you're taking a move, making a move on the board. Now you could make a move which could either boost you or actually take you backward, or maybe I don't know how to really explain in depth, but it has to be someone who knows how to play chess can actually understand. So if you make a wrong move, remember they're going to take your pawn off the board, and that will be a loss on your side. But if you learn how to navigate this board, with time you'll be getting rewards only. That is when you have wins and you're taking your opponent's pawns off the board. Those are all rewards. But when you make a wrong move, you face a penalty. That is when your pawn is thrown off the board. Then policy, I already explained um policy is just like a strategy, or maybe okay, a strategy that helps you to a strategy that helps you to take an action. So next, I'm going to be explaining the code. So the first part of the code, here we're going to do an implementation in MDP. So we have this first part of import numpy as NP. So what we're doing there basically is we are importing to handle numerical operations efficiently. Then the next thing we are doing here on define MDP so and so, we are now just defining the states. So we know this MDP has 5 states, 0 to 4. Then we have 2 possible actions, either 0 and 1, which can be taken per state. So the next part of our code, here we are explaining the transition probabilities. So what we know here in this code is the S and the A define the transition probabilities taken when taking an action A in a state S. Then we also have the transition. Okay, just something to tell you something about this transition. It's deterministic. It's deterministic. Then the next part of our code, which is the reward function. So basically there, what we are dealing with is we are specifying the reward received when taking an action A in state S. For example, if you take an action 0 in state 0, you're given a reward of 5. When you take an action 1 in state 0, so when you take action 1 in state 0, you get a reward of 10. So our next part of the code, we have initializing the value function and the policy v what and what. So let me just give you a brief explanation of what this part is about. So here, basically the part where we have v is, we know it stores the estimated, here this we are basically storing the estimated value of each state. So the next part where we have the MDP evaluation, here where we have the MDP evaluation, sorry. So here we're just computing the function iteratively. I think we already know what iteratively means, continuously. So now here at policy improvement, we've like we see here, choose the best action based on this and this. So here what we're doing is we're getting the optimal policy, or the optimal policy is determined by maybe selecting an action A that maximizes the value function. Then we have our last part of the code, which has print results. So here what we are doing, basically we're just displaying the computed optimal state values and the best actions to take in each of the states. So here now, previously I was just explaining for you the different parts of the code. So here I'm just going to summarize for you what exactly this code has. So we've established it defines an MDP with states, actions, transition probabilities, and rewards. So it now computes that value function using the Bellman's equation iteratively. Then we do know that it derives the optimal policy, or it gets the optimal policy based on the computed values. Then for the last part, we know that it prints or outputs the optimal policy, showing best action for each state. But you can say uses, or okay, here at this state, we are going to use the Bellman equation to determine the state values. There's also that part. There is where we derive the optimal policy based on the computed values. So to give you a conclusion of our findings or our research on reinforcement learning. So basically, we know reinforcement learning is a category under machine learning. We've already established that. We know it has two types under it, the model-based and the model-free. Now to go deep into the model-free, sorry, let me take you back a bit. We know it has concepts. We have state, the state. We already gave the definition, the environment, the policy. We have an agent, and then let me now take into the types of reinforcement learning. So we have model-based, and then we have model-free. Already established that. So we already established that under the model-based, here the agent is working in an environment which they already have, okay, which they are familiar with. So it's easier for them to follow policies or strategies to get an optimal value or to reach an optimal state. Whereas with the model free, the agent is taking actions and learning, interacting with an environment which they have where they have no clue about the environment. Let me give you a real life example. Let me say we have a camera surveillance, a robot surveillance, which is for traffic. Let me say traffic, and we just place it in some area. Now that is a dynamic environment. What I mean by dynamic, the robot, even us in particular, we cannot really establish everything that is going on in that environment. For example, the weather changes and all those things. So now this robot has to learn on its own. So that is a model-free based algorithm under reinforcement learning. Then we've also established that reinforcement learning it's not categorized to supervised or unsupervised because it falls under both categories. When we see that we have model-based and model-free now, I assume in model-based, that's where we could be applying supervised learning. And then in model-free, we could be practicing the unsupervised learning. So we can say reinforcement learning falls in both the categories. So we know just the main thing with reinforcement learning is just an agent, which could be a robot learning from its environment. It first interacts with this environment, learns from it, then it makes its own policies to follow so that it gets optimal rewards or rewards, penalties, whatever it derives from carrying out actions. Then it now has to train itself, or it learns and trains itself to now follow a policy or follow a strategy or follow a route to get to an optimal solution, an optimal value, or an optimal path. Yes. So thank you so much.
Welcome.